For example 10, I'm going to start with the example already filled out and talk about it. I want to know what you think about that as opposed to the way I normally construct the videos. But anyway, here we are, Packet 9A, page 5. Key questions: what is the series? Second one, does the series converge? If so, where? And then, keeping in mind, what have we learned so far? We've already learned how to generate a series using the template, okay, which is the one we're going to start with here. But in this video, we're going to talk about how to generate a new series using differentiation as well as integration, and two other methods that are commonly used. So let's go ahead and get started. Here we see again rational function on the left, infinite series of polynomial terms on the right. We know that this series is equal to the rational function for values of x whose absolute value is less than 1. But when we differentiate the left side, we get 1 over 1 minus x squared. Okay, and when we differentiate the right side, if you remember, when you differentiate a polynomial function, you're differentiating every single term separately or individually. And so it's no different when we differentiate in infinite series. We're just going to differentiate term by term. So let's go ahead and do that. The derivative of 1 is 0, so we're not even going to write that. Derivative of x is 1, plus the derivative of x squared, 2x, plus derivative of x cubed, 3x squared, and so on, plus dot dot dot, and plus the derivative of x to the nth power is just the exponent out front multiplied by x to the exponent minus 1, just the way we learned way back when using the power rule, and the power being n doesn't change anything, as you can see. Okay, plus dot 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 equals, and then we have we want to make sure we practice the integral, or the sigma notation. We have n starting at 1 going to infinity, and we have n times x to the n minus 1, which I always check. Okay, put the 1 in for n in both places here. We have 1 times x to the 1 minus 1, so we have 1 times x to the 0, which is just 1. That's our first term, check. If you replace n with 2, just to make sure, 2 times x to the first power, and we get 2x, check. So we've got our correct sigma notation. And one thing to notice, or to make note of, is that the new series will converge over the same interval as the original series. And so we already knew that the original series converged for values of x whose absolute value is less than 1. So this new series will also converge over the same interval of real numbers. Okay, so that's very helpful. So let's look at example 11. So for example 11, we want to find a power series representation for f prime of x given to us with the sigma notation. Please make note that the exponent of the x, okay, is an n, not an x. That was a typo. So if we write out the series expansion here, instead of using sigma notation, we could get maybe a better picture of how to differentiate each term. And so let's go ahead and do that. F prime of x is equal to, again, we're differentiating each term, term by term. The derivative of 1 is 0. Derivative of 3x is 3. The derivative of, now I could write this as 9x squared. I probably should, but it's kind of nice to keep the pattern going. So I'm gonna do that. I'm gonna write 2 times 3 squared times x to the 2 minus 1. Okay, and then plus, and then we have 3 times 3 cubed times x to the 3 minus 1 is 2. Okay, that helps me get my nth term. Not that I necessarily would need that right now, because here we see 3 to the n, so we can write n times 3 to the n times x to the n minus 1. Okay, so we've got that, and then plus dot dot dot, which is equal to, and we're going to start n at something, and let's just see, if we put n equals 0, if we start it at n equals 0, then this is just going to be 0 times something, and so that's not going to be any fun. So let's start at n equals 1. So we have 1 times 3, just trying to make sure we just get 3 here, times x to the 0, so we just get 3. So we're going to start n at 1, and we're just going to use our Okay, so there we have our sigma. And that's about all we need to do for that. Okay, so let's go ahead and take a look at the next one. Okay, let's see what happens if we integrate instead of differentiate. So we've got that same function. When we integrate both sides, this guy here, if we want to find an antiderivative of 1 over 1 minus x, don't make that careless error of just saying it's ln of 1 minus x, or even ln of absolute value of 1 minus x, okay? This is a u sub. Okay, so a quick reminder of how to do this. U equals 1 minus x. Du is negative dx. Okay, so we get negative du for our dx. And that's why we get a minus sign out here, and we get minus ln of the absolute value of 1 minus x. Okay, integrate 1 over u, but it's negative integral of 1 over u, so it's negative ln of the u, which is, or absolute value of the u, which is 1 minus x. Okay, that's why we get the minus sign there. So you've been taught that, you know that, don't get careless. Okay, not a time to get careless. Get careless after May 5th. All right, and then integrating both sides here. Again, we're integrating term by term, and integrating 1. Now again, you got to go the other direction now. We know the antiderivative of 1 is x. Okay, and then the antiderivative of x is x squared over 2, and then we have plus x cubed over 3 plus x to the 4th over 4 plus dot dot dot, and then plus x to the n x to the n plus 1 over n plus 1, and then plus dot dot dot. Always make sure if you put an equal sign there that you include the plus dot 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 at the very end, because then it shows that this is equal to this infinite series. Okay, so what do you think will be the interval of convergence? Well, if you thought that the interval of convergence would be the same as the original series, then you'd be right, because we already talked about that. The new series will converge over the same interval as the original series, and we already know that the original series interval of convergence is that. So we have the same thing. Okay? And if you like to write it like this, go right ahead. Those mean the same thing. Or, okay, those mean the same thing. So I will start a new video for the next page, and then we will be done for the day.